Okay, you guys. So here we go. We had done this example in class, so I still have it written up. It says example 2, I guess for the purposes of this would be example 1. And this is one where you can't use Big Mama, 1 over 1 minus x. Incidentally, you guys did great on the quiz. I was so excited. I was in the dermatology office and I was grading away and getting happier and happier. So she saw me and she's like, well, she really didn't say this, but I'm sure she was wondering, why is this woman so happy? She is grading papers every time she's here, which is odd, but fun. Okay, anyway, so Big Mama, but I like Big Mama. Big Mama. She produces children where if you substitute stuff in for x, like maybe x cubed or negative x, it can produce all these children and cousins and second cousins once removed and things like that, that have a radius of convergence of negative 1 to 1 as long as the coefficient here is 1 or negative 1. So we talked about that. Now that does not work for transcendental functions. So if you've got sine or cosine or ln x or e to the x or kitties that sit on your uh, tablet, which my big fat cat just came down and thought that would be a fun place to sit. Um, this won't work for them. So we developed series for cosine, sine, and e to the x, and then I just said here, know the rest of these. So this one took you through it. We don't really need to be taken through it because we already did this in a previous example. Substitute x cubed in, blah blah blah. Do it in the general term. Simplify in case you're on the what is it called? The multiple choice section of the AP. Otherwise, for me, you could leave it here. You could even leave it here. I don't care. I can do math often. So um, that's just a recap of that. You have to memorize these. This is the bank of functions for which you're responsible on the AP. They don't give you time to bust out, the general one and then substitute stuff in. You absolutely won't have the time to do it. So you have to commit these to memory. If you don't like memorizing, I don't have a suggestion. You just have to decide to do it. So the nice part about math is you don't have to like it. Isn't that cool? You just do it. You don't have to like it. Interval of convergencies, whatever it's called, those are also important. So you have to know those. Where does it converge? And notice my very, very, very favorites are e to the x, sine x, and cosine x. And I think I showed you that graphic that shows you the polynomials that flip-flop, 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 and eventually match exactly those three functions. So it's beautiful. You don't have to worry about a center because it's going to be happy everywhere. All right. So as I just said, for sine x cubed, you substitute in x cubed. For cosine 2x, if it's a square root, you substitute in square root of 2x. I'll do this just so that you can see one more example in case this is fuzzy to you and you don't remember what in the world we did. So I write out the cosine, and general cosine 1 starts with 1 minus x squared over 2 factorial plus, I don't want to take all day on this one, but I'm going to write out a couple of terms. 4 factorial x to the 6th over 6 factorial. We mentioned also that it's appropriate and not a surprise at all that these are even exponents, even factorials. Why? And I just realized I messed up my signs. This is why I should not talk and write. That one's cool. This one is not. Neither is that one. Okay, because these are alternating. And we already saw that when we developed it. But what I was saying is that it's appropriate these are even powers because cosine is an even function. Remember even versus odd functions. Here is cosine, the actual just cosine function. It can be folded like a sandwich over the y-axis, right? So this side perfectly matches this side, right? Odd functions you would expect to have opposites, right? It's symmetric with respect to the origin. So this guy is even, just like cosine is even. So is our parabolas just x squared. X cubed would work like this odd function, right? So everything's tied together in math. There's no reason or there's no accidental math, right? They all fit together. So here I got an odd function. Check it out. I got all odd powers. Here I've got, oh gosh, I did something weird, an even function. So anyway, let's look at substituting square root of 2x. So I've got cosine square root of 2x, and I'm going to just substitute that in, and I'm going to change it to x to the 1/2, 2x to the 1/2. So 2x to the 1/2 squared, because I like to multiply exponents rather than have to think in my little brain what is going on. So this is plus 2x to the 1/2 to the 4th minus 2x, and this should be 2x to the 1/2 included, right? So I'm kind of like being sloppy up here. This is to the 8th. So this is really, this should have a parentheses around it. The first one was fine. Over 6 factorial. Blah, blah, blah. You get the point. So in general, I would say this is negative 1 to the n, so that it flips sign, x to the 2n all over 2n factorial, but that's not this one, right? That's just the general one. If I substitute 2x in there, I'm going to get the sum from 0 to infinity of negative 1 to the n, square root of 2x to the 2n all over 2n factorial. And then you can goof around with that if you like. So you would know that this is 2x to the n, because this is x to the 1/2, and then if you multiply that by 2, it pops that off. So, and then variations on the theme, and 2n factorial. Did you hear my kitty? She's a little upset because I won't let her do math today. She's pretty smart. You know, she knows all the way up to D in her alphabet. So we're pretty good with that. Eventually she's going to know numbers, both Arabic and Roman. Oh dear, she thinks it's a good plan to be next to the computer. Anyway, so example 4 says grab e to the x and substitute x squared. Example 5 says grab sine x and pop in x over 2. Simple, simple. The one that is not so simple, or perhaps would not occur to you, would be the next example. And the next example is sine squared x. And the temptation is to say, I'm going to bust out sine, I'm going to square that puppy, and I'm done. And you do not want to square puppies. And you don't want to square sine. So do not square a series. So do not. That's like a devil thing to do. Boo. Do not square a series. Do not square a series. You could make a little song out of that. Okay. Okay, just like squaring a number is not the same as multiplying it by 2, unless your number happens to be 2. But squaring 6 is not like 2 times 6. So you cannot just square a series. No squaring. So we have to come up with a way to simply substitute, and this is where your fun pre-calc early childhood math comes in. So all those flashcards you threw away, you might want to dig them out or rewrite them. Because sine squared comes from the double angle formula, or I should say the double angle formula is related to sine squared. And so this allows you to break up sine squared into cosine 2x over 2 and then 1 over 2, subtracting those. So let's do it. So sine squared x is not a squared series. It is simply 1/2 minus, I'm going to make this 1/2 cosine 2x. Okay? And so we can substitute in 2x, multiply it by 1/2, just keep that first term. So it's going to be 1/2 minus 1/2. I'm popping in 2x for cosine. So I have 1/2 minus 1/2 plus 4x squared. Maybe I should do this in general. Would that be a fun thing to do? I don't know. Perhaps it would be. So let me give you the general formula somewhere so you can see what in the heck I'm doing. Although this is just like the one we did above. Okay, so here is happy cosine. cosine of x. You're going to be tired of me writing this, aren't you? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus blah blah blah. Okay, so if I do this, I'm going to have 1/2 from this guy minus 1/2 times 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus 2x to the 8th over 8 factorial minus blah blah blah. Okay, and then I can distribute the 1/2, and notice it's going to switch the signs because it's a negative 1/2. So I'm just going to change this to negative 1 over 2. This is going to be plus, there's going to be a 2 on the bottom. This is going to turn to minus. There's going to be a 2 on the bottom. This is going to change to plus with a 2 on the bottom. This is going to change to minus with a 2 on the bottom. So if I do this in the general form, I'm going to have, now I'm going to leave it the original way, 1/2 minus 1/2 times the sum from 0 to infinity of, let's see, I need it alternating, negative 1 to the n, 2x to the 2n all over 2, well, I'll change that in just a second. It'll be 2x factorial. If I distribute the 1/2 in there, and this time I'm not going to distribute the negative with it. I'll leave the negative on the outside so that I don't have to mess with the n plus 1 for negative 1. So 1/2 minus the sum of, I'm just trying to keep it as simple as possible, 2x, I'm just going to leave this 2x to the 2n, all over 2 times 2x factorial. Done. Done, 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 and ready for fun. There we go. It could either be this, or it could be its friend up below. Whoops, I missed the 2n. Maybe I'll just erase that. That would be fun. Okay, so you get the point, I think. The punchline is down here. 1/2 minus the sum, blah, blah, blah. And I should put the limits of the sum also. Not that they're really limited, but it starts at 0 and goes to infinity. And my goal is to make sure that this is correct. There are different ways that you can write this. So I always check out the first term or two. So if I put in 1/2 minus, if I put 0 in for all of my n's, that's going to be the sum of negative 1 to the 0, 2x to the 0, over 2 times 0 factorial. And 0 factorial is 1. Someday I will show you why that is 1. It's great fun. You can also Google it. You can also look up YouTube. There are some fun videos. They do it sometimes in general. Sometimes they just suggest a pattern. But this will give you that first number, which is 1/2. Everything else is going to cancel for this. So it's going to be minus 1/2. And then you're going to generate the rest of the series. So check it out. Make sure it works for the first term. All right. Done and ready for fun. The next one is a very interesting problem. There was one like this on the AP maybe 2 years back, where they said, I want the integral, and it's a definite integral. So that means I'm looking for a number. However, we have a power series. So the question is, well, how do I get a number? Well, you can't really get a number unless you say, I want it to be limited somewhere. Well, you could get a number. It's just not going to necessarily be very precise. So this says, I want an error of 0.01. All right, so that means how many terms do I carry it out to get an error of 0.01? I don't know. We're not in 1 over 1 minus x land anymore, right? So I'm really not sure how to do this, but let's write it out. I know that e to the x is 1 plus x plus, so these are all pluses, all adding, 2 factorial plus x cubed over 3 factorial. And I'm going to write out enough of these so that we have it. You're not sure why probably right now, but that's okay. X to the 4th over 4 factorial. I got x to the 6th over 6 factorial. What did I do? It's x to the 5th, isn't it? We just go up by 1. Okay, so x to the 5th over 5 factorial. I got x to the 6th over 6 factorial. I'm going to erase this stuff right here because I want to go out, and you'll see why in just a second. I got x to the 7th over 7 factorial. I got x to the 8th. This is just the general one. 8 factorial plus blah, blah, blah. Okay. Now I'm substituting in negative x squared. Don't panic. Just substitute it in. I'm going to pick a different color. How about green? So e to the negative x squared. So the 1 doesn't change. There is no x plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial plus negative x to the 4th over 4 factorial. Some of you resist writing these out. You resist. You're part of the resistance. And I forgot my square, didn't I? See, that's why I make mistakes. I make little jokes in my head, and then I forget what I'm doing. This is the 5th over 5 factorial. I think this is like the 5th time I've recorded this because I kept making errors because I keep talking just like I'm doing now. Why do I do this? I don't know. It's frustrating, kind of. But I amuse myself. Sometimes I amuse other people too, but probably not often because my jokes are so stupid. They're just whatever rolls out of my head at 6 o'clock in the morning. All right. So, here we go. I am integrating that. So, let me write it out without the parentheses, so that for me at least it's easier to integrate. So, here we go. So I got negative x squared. This will be plus x to the 6th over 2 factorial minus x to the, that would often be 4, right? 2 times 2 is usually 4. This is x to the 6th over 3 factorial. Notice the sign is negative because I'm raising it to a 3rd power. This guy will be positive, x to the 8th over 4 factorial minus x to the 10th over 5 factorial. So notice I now have 2, 4, 6, 8. What started out as 1, 2, 3, 4, 5 is now doubling. And that's fine. We like doubling things. X to the 10th. How about plus x to the 12th over 6 factorial minus x to the 7th over, just kidding, that's x to the 14th, right? X to the 14th over 7 factorial. Now, I could keep on going. It would be great fun to do so. But I'm integrating this. Okay, so I'm integrating this series. So don't forget what you're doing. And I'm trying to go from 0 to 1. So when I do that, I'm going to put example 8 on a different page because it's too squishy here. I'm going to get x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial. There's a lag in this. This poor computer has been on far too long. This is plus x to the 9th over 9 times 4 factorial. And then minus x to the 11th. So now I'm producing things that are odd powers. How fun is that? See, x to the ninth, x to the 11th over 5 factorial plus x to the 13th. And you might say, woman, why are you going out so far? And it's just because it's fun. 6 factorial minus blah, blah, blah. Okay, so we have the integral. It's a definite integral for which I need to know where to stop. I'm going from 0 to 1. Now the pretty part about this is if I were to substitute a 0 in for all of these guys, they're going to cancel. So I don't have to worry about the 0. What I really need to do is think about 1. And the question is, where do I stop to limit my error to 0.01? Well, back in the alternating series section, we said if something is alternating, there's an error bound, which is really easy to find. What I do is I evaluate terms until I get to a value for the actual term that is smaller than the error that I want, which is why I wrote out so many terms, because I'm not sure where to stop. So I need to put a 1, 1, 1, 1, 1, 1, 1 in here, and I'm looking for the term that is less than 0.01, its value. Whatever that is, let's say it's x to the 13th. And I put everything in, and that's finally less than 0.01. Chop that term off and add the previous terms before it. So we're not going to use the term that is that value. We chop it, use everybody else. So let's do it. I'm going to substitute 1 for x. Clearly that is way too big. 1/3 is way too big. 1, what is that, 10th is way too big. That's 0.1. This is 1 over 42. Okay, so the question is, what is the value of 1 over 42? Well, it's 0.023. Still too big. X to the 9th, and remember that's a 9. It's kind of hard to read. Not that it matters because we're putting a 1 in there. That one, 0.004629. Whoa, I am way happy. That is smaller than 0.01. So we chop off that term, and I add all of this. So if I add all of that up, I get 0.74285. This is a decimal point, so 0.74285. 7149. And we're saying that is within 0.01 of the actual sum. If I had summed that thing, if I had added forever and ever, that's going to be within 0.01 of the actual sum. Now, the true answer, now it's not really true. If you use Calculator Man, remember, all he's doing is the same thing you're doing. He's just doing it for a longer period of time, right? Mr. 9-pack here. Okay, he's pretty excited about this because he knows more terms than you do. So what he's going to tell you is something so similar. What you've done in the calculator is you put in, give me the integral from 0 to 1 of e to the negative x squared, and do it forever, dx. So he's not really doing it forever. He's doing it however many terms it's programmed for. If you do that one, that is 0.7468 241 328. And if you subtract those, you're looking at the error, I'm getting about 0.003. I only needed 0.01. So that is the error between what the calculator tells you, again, it's only an estimate, and your value, which is pretty darn good. We've only used 4 terms. Sometimes the AP will say, how many terms do you need to add? You would just say 4, first 4. It doesn't mean go up to the 4th. It means just give me the first 4 terms. X, x cubed, x5, x to the 7th. Other times it'll say, now use the first 4 terms to find the sum. And that's what you would say. Great question, because it requires that you know Taylor plus the alternating series test. And often on the what is it called, the free response, they squish everything in that they possibly can from the entire course. So you got to know what you're doing. Okay, the last one, if this will turn the page or give me a new page. The last one is something that people have asked me throughout the years, and um, I've said, it's just a long story. I don't know. So e to the I pi. I've had this written on my board so many times. E to the I pi is -1. And then people come up to me, why is e to the I pi -1? So this example, example 8, is saying e to the I pi plus 1 equals 0. So we're proving that, but really all I need to do is prove that e to the I pi is -1. And the question is why? Well, let's bust out the series for e to the x. So I'm tired of writing this. You're tired of writing this. It's great to be tired of writing a series. 1 plus x squared over 2 factorial plus, I wish I just had a copy paste for this, right? It would be so much simpler. But boredom is good in this case. X to the 5th. And I'm writing out enough terms because I know where we're going with this. You might not know. You might write the first 2 terms and then you won't see the pattern. And oftentimes math is about patterns. You look at a pattern and you say, oh, holy cow. The cows are holy. X to the 7th over 7 factorial. Maybe I'll stop there. I'm kind of out of room. Okay. So I'm substituting in I pi. Okay, kind of like I spy. Only it's I pi. 1 plus I pi plus, so don't be alarmed if you have an I in there. That is the imaginary unit. So when I square it, it's going to be -1. See all that algebra 2 stuff that you did? It was not for naught. I pi cubed, which of course you know because you're smarty pants, that that's just going to result in an I, right? I cubed is just -I. Plus, so here we get to the term for I to the 4th, which is simply 1. Remember, this repeats in in groups of 4. So, and I'm sure you derived that in algebra 2. If you didn't, that's okay. No worries. 5 factorial plus I pi, I pi to the 6th over 6 factorial. I'm going to try to squish that 7 in there. I pi to the 7th over the fabulous, ever popular 7 factorial, blah, blah, blah. Okay, so I'm going to simplify these using powers of I. And remember the pattern for I. So I is just I. There's nothing I can do. It's square root of -1, but we're just going to say I is I. I squared is -1. I cubed is -I. And I to the 4th is simply 1. So when you used to do this and you had I to the 57th, you would divide by 4 to find out how many 1s are in there, and then you would use whatever's left over. Okay, but these ones are pretty simple. So this is I pi that we're substituting in. So e to the I pi is 1 plus I pi minus pi over 2 factorial. I cubed is -1. So negative I pi over 3 factorial plus, now the I is gone. So I get pi over 4 over, pi over 4 factorial. And then the 5 repeats the I. So I've got I pi to the 5th. And I'm forgetting my powers, aren't I? I pi, this is pi squared, this is pi cubed, this is pi to the 4th. So the pi's don't cancel, they don't do anything weird, they just continue. So 4 I pi to the 5th over 5 factorial plus I to the sixth again is negative 1. So I could put a negative in here instead of a positive. Let's see. I to the fourth, I to the fifth. I to the sixth is negative 1. So I just get negative pi over to the sixth over 6 factorial plus I pi to the seventh over 7 factorial. So assuming I did not talk over myself to the extent that I made some silly error, I'm just going to look and make sure we got it. So I substituted in I pi. Here it doesn't matter. Here it does matter. Here it matters. It produces negative 1. This one produces negative I. This is 1. And then we continue on. This is going to leave an I. That's going to leave a negative 1. This is going to leave a negative I. Oh, negative I. See? See, senor. Okay. All right. So, because I to the seventh is the same as I cubed, which is negative I. Okay. I'm going to group these. I'm going to group them so that my evens are together. So I've got 1 minus pi squared over 2 factorial plus pi to the fourth over 4 factorial, just rearranging them, minus pi to the sixth over 6 factorial plus blah blah blah. So that's one set, and to that I'm going to add the odds. So I pi minus I pi cubed over 3 factorial plus, it's a great extra credit question, I pi to the fifth over 5 factorial minus I pi to the seventh over 7 factorial, blah blah blah. And then it's a recognition problem. You're going to look at this and say, holy cow, cows are holy. This is just cosine of pi, right? Cosine of pi. Clearly it was cosine, I substituted in pi. Plus, this guy is simply sine I pi. So I could say I sine pi. Wow, that's if I were to take the i's out and then I just get sine. And the question is, what is that equal to? Well, sine of pi is 0. Cosine of pi is negative 1. So e to the I pi is truly negative 1, which is what we wanted. E to the I pi is negative 1. Their question was e to the I pi plus 1 equals 0. Well, I got negative 1 plus 1 is often 0. Done. So in my first period, I made a sign error, so it was working out weirdly, but that is the actual proof. Okay, so have fun. What we're going to do is, if this will turn the page, I think I turned 2 pages at once, actually. Maybe not. Okay, so you got the homework for Taylor and McLaurin. I will upload that so that you have the answers. And then we go on to something that I've actually already worked out. There's already a video on this. So Lagrange error, this is the error for Taylor polynomials. Like if you don't have an alternating series, so you can't use the alternating series error, there is a formula which looks big and scary, but it's actually not bad. Okay, so have a fun day, and I will be with you on the flip side. Okay, ciao ciao.